Hello everyone, today we'll be presenting the design of a chlorinated hydrocarbon heat exchanger. This is a project developed by us, Group 15, focusing on the cooling of a corrosive process steam using a shell and tube heat exchanger. Now let's briefly introduce the team. We are Amira Naziha, Balkis, Farah Batrisha, which is me, and Muhammad Afif Mutaki. And each of us contributed equally to different aspects of this project. And now let's get into the details.
Now, I will present the design specification for our heat exchanger E101. The process stream consists of chlorinated hydrocarbons, which is CH3Cl, HCl, Cl2, and CCl4. The process fluid is cooled from 100 degree to 28 degree, while the cooling water temperature increases from 25 degree to 35 degree. The mixed flow rate of the process stream is 0.366 kg per second, with a required heat duty of 3 to 2 kilowatts. The main objective of this design is to develop a shell and tube heat exchanger that can safely and efficiently cool the chlorinated hydrocarbon mixture to the desired outlet temperature. Working principles, this heat exchanger transfer heat by convection from the hot process stream to the tube walls and then to the cooling water, while conduction through the metal wall follows Fourier's law. All thermal resistance, including fouling, are combined in the overall heat transfer coefficient, which is U, which we use with LMTD and NTU methods to relate heat duty, temperature change, and required area. Now, I will present the purpose and configuration. E101 cools the process stream from 100 degree to 28 degree for downstream operations, while improving safety by reducing corrosion, decomposition, and vapor pressure, and recovering about 322 kilowatt of heat. It is a one shell pass, two tube pass countercurrent shell and tube exchanger with segmental baffles, 3/4 inches scheduled AP, SS31CL tubes of 10 meter length, and a carbon steel shell with corrosion allowance. Next, I will present the Excel sheet. This Excel sheet is used to check whether our chosen shell and tube heat exchanger design can really deliver the required heat duty. It calculates flow properties and Reynolds numbers in the tubes and shell. Then, use correlation to find the inside and outside heat transfer coefficients. With this, plus the tube material, length, and volume factors, it combines all resistance into the overall coefficient U and estimate the needed number of tubes. In short, this calculation confirms that the exchanger geometry and operating conditions are sufficient and realistic for our cooling duty. I will present the Excel analysis result for the heat exchanger design. The calculated heat duty is 322.34 kilowatts with an overall heat transfer coefficient of 0.844 watt per square meter Kelvin. The heat capacity rate of the hot stream is 4.48 kilowatt per Kelvin, while the cold stream has a lower value of 1.67 kilowatt per Kelvin, indicating that the cold stream is the limiting side. A fouling factor of 0.0001 square meter Kelvin per watt was applied to ensure realistic operating conditions. The exchanger consists of 6 tubes, each with a length of 10 meters. All calculations were carried out using the effectiveness NTU method, supported by convective heat transfer correlations, pressure drop calculations, and performance verification.
Now I will continue for the heat exchanger E101 schematic. So I will explain the cross-sectional area first. The diameter inner is 0.03814 and the diameter outer is 0.03814. The thickness between the two tubes is 0.05. So we use the shell and tube heat exchanger and they have 8 parts in the heat exchanger. First is input, output, and the third one is fluid input and fluid output, and next tube sheet, baffle, tube, and the last one is shell, and the length of the shell is 10 meter. Next, I will explain the main feature of a heat exchanger, focusing on a shell and tube type. First, we have the shell with inlet and outlet nozzle. the shell is the outer casing of the heat exchanger, and the nozzle allows the working fluid to enter to leave the system. This ensures control flow and proper heat transfer between fluids. Next is the tube bundle arrangement. Inside the shell, multiple tubes are arranged in a bundle. One fluid flow inside the tube while the other flow outside the tube but within the shell. This arrangement increases the surface area, which improves heat transfer efficiency. The tube sheet and channel heads are also important components. The tube sheet hold the tube firmly in place, while this channel head direct the fluid into the tube. This part also make maintenance and cleaning easier. Another key feature is the baffle configuration. Baffles are placed inside the shell to guide the shell side fluid across the tube rather than straight through. This increases turbulence and enhances heat transfer. We also have support structure which prevent the tube from vibrating or sagging during operation. This helps extend the equipment lifespan. Finally, flow direction indicators show the direction of fluid movement, ensuring correct the operation and safe handling. Overall, these features work together to ensure efficient, safe, and reliable heat exchange. Next, we will go on to the next topic, which is the challenge related to material selection for the heat exchanger. The system operates in a corrosive environment involving hydrochloric acid and wet chlorine. With temperature ranging from 28 degrees Celsius to 100 degrees Celsius, this condition can cause severe corrosion if an unsuitable material in use. To overcome this, stainless steel 316 liter was selected. It offers excellent resistance to chloride corrosion, perform well within the operating temperature range, and provide better durability in high temperature areas. These are also special design consideration. The two tube sheet joints are critical and require careful design, while the high temperature inlet region needs extra protection. Additionally, preventing stress corrosion cracking is essential in chloride-rich environment. Overall, stainless steel 316 liter ensures safe, reliable, and long-term operation of the heat exchanger.
So this slide shows our design challenge, which focuses on energy optimization. So firstly, we have temperature management. The process requires a large temperature difference of about 72 degrees Celsius for cooling. So to manage this efficiently, we use practical temperature differences so the system can transfer heat effectively without wasting energy. So the cooling water temperature increase is kept at around 10 degrees Celsius to ensure efficient heat removal while saving cooling water. So next is flow optimization. So we use counter-current flow arrangement because it improves heat transfer efficiency. So a two-pass design is applied to increase fluid velocity inside the tubes, which helps enhance heat transfer. The baffle spacing is also adjusted to reduce pressure drop while maintaining good performance. Lastly is fouling management. A fouling factor is included in this design to account for dirt buildup over time. So extra performance margin is added so the system can still work well even with fouling. Regular maintenance is planned to keep the system operating efficiently. Overall, this design balances energy efficiency, performance, and also long-term operation. So now we focus on safety integration in the design. So the system is designed to operate safely at high temperatures with components rated up to 100 degrees Celsius and allowance for thermal expansion along with regular inspection. It also follows ASME standards for pressure containment, includes pressure relief valve on both sides, and has safety margins across the operating range. So to prevent leaks, double sealed joints and strong welding techniques are used. And finally, temperature and pressure are monitored continuously to allow early detection of any issues. Overall, these measures ensure safe and reliable operation. So, to summarize, this design can effectively handle a corrosive chlorinated stream. It achieves a temperature reduction of 72 degrees Celsius with an efficient 10 degrees Celsius cooling water temperature rise. The system is robust, reliable for long-term operation, and complies with relevant industry standards. Overall, the design meets both performance and safety requirements.
That's all from us. Thank you for watching.